This lecture is on the hemodynamics of coronary vascular steel. And by the end of this lecture, the student should be able to first describe the relationship between flow, pressure, and resistance. Secondly, the student should be able to describe the parallel and series arrangement of coronary arteries and the hemodynamic significance of this arrangement. And finally, you should be able to describe how one or more arterial stenotic lesions affect the distribution of coronary flow at rest and during conditions that promote coronary vasodilation. Let's begin by looking at the relationship between pressure and flow and resistance in an isolated arterial vascular segment. In this lecture, I will be assuming that we are operating under laminar non-turbulent flow conditions. So we have a vessel here, an arterial segment, and we have a certain flow that is passing through that vessel. Well, the flow through this vessel, because it is against a resistance, which I'll describe in more detail in the next slide, will generate a pressure drop along the length of that vessel. So there'll be a certain inlet pressure and an outlet pressure somewhere further down the vessel length. It turns out that the pressure drop, or this pressure gradient, is equal to the flow through that vessel times the resistance to flow of that vascular segment. Therefore, increasing either the flow or the resistance of the vessel will increase the pressure gradient or difference between the input and the output of this vascular segment. It's important to note that in a normal artery, normal large distributing arteries such as the epicardial coronary vessels or other large vessels in the body, the pressure gradient along their length is very, very small. It's usually less than 1 millimeter of mercury. And the reason for that is that the resistance is very low relative to the flow rate inside the vessel. So therefore the delta P is very low along its length. Now let's look in a little bit more detail at what determines the resistance to flow in this blood vessel. Well, it turns out that the resistance to flow is directly related to the length of the vessel, L, times the viscosity of the blood that is perfusing the vessel. And the viscosity is largely determined by the hematocrit. And the resistance is inversely related to the diameter of the vessel, but to the fourth power. Now, normally, length of a vessel does not change appreciably, and the viscosity of the blood is normally relatively constant. So physiologically, the most important factor that determines the resistance to flow within the vessel is the diameter of the vessel. And so we can simplify this by saying that resistance is proportionate to 1 over the diameter to the fourth power. This means that if we were to decrease the diameter of this vessel by 50%, so 1/2 the original diameter, because this changes to the fourth power, that means that resistance will increase 1/2 to the fourth power. So it's going to be 16-fold increase in resistance. Therefore, very small changes in diameter cause very large changes in resistance to blood flow. In the last 2 slides, we have looked at the relationship between pressure, flow, and resistance in an isolated arterial segment. But normally that arterial segment is perfusing a region of tissue. So the arterial segment then is dividing into smaller arteries and eventually arterioles that will make up the microvascular network of that tissue. The flow through that tissue is determined by the perfusion gradient across that tissue, which would be normally the arterial pressure minus the venous pressure, and that's our delta P. And then the resistance of the distributing artery plus the vascular resistance, that sum would be the total resistance. So now we can say that the flow through a tissue segment is going to be equal to some driving pressure divided by the resistance. And furthermore, that driving pressure is normally the arterial minus the venous pressure divided by the resistance of that tissue unit. With this slide, I want to illustrate an important principle regarding series resistance units. The large artery is said to be in series with the vascular element that it is perfusing because the blood flow is flowing from that proximal artery into the tissue and being distributed. So we really have two separate resistance elements. We have the resistance of the feed artery, the distributing artery, and we have the resistance of all the microcirculatory vessels that comprise the vascular bed that is being perfused by that distributing artery. And because the total resistance is equal to the sum of the large artery resistance plus the small vascular artery resistance, so RT is equal to R sub L plus R sub S, we can now substitute and say that flow through that vascular bed is equal to some driving pressure, arterial minus venous, divided by the resistance of the feed artery plus the resistance of the microcirculation of the vascular bed that's being supplied by the feed artery. I said in an earlier slide that normally the distributing artery has a very low resistance. It's approximately 1% of the total resistance of this unit. And because it comprises such a small fraction of the total resistance, diameter reductions must be very large in order to significantly affect the overall resistance. And that can be shown quantitatively by plugging in some numbers here. If we assume that the large artery resistance is 1% of the total resistance, we can now say that flow is equal to delta P divided by 0.01 times the total resistance, that's the large vessel resistance, plus the small vessel resistance, which would be 0.99 times the total resistance. And you can see from this that this is just 1% of the total resistance. And if, for example, we were to increase the resistance of this vessel along its entire length, reducing its diameter to 1/2 normal, that would cause a 16-fold increase in the resistance. Well, that 16-fold increase in resistance would change this number from 0.01 to 0.16. And if you add that to 0.99, you'd have 1.15 times total resistance, meaning that the total resistance is only increased by 15% when you have a 16-fold increase in the resistance of the feed artery. And that is the reason why you have to have very large reductions in diameter of a feed artery in order to have a significant effect on the overall resistance and flow in the vascular bed that is being supplied by that feed artery. Now let's move away from kind of this hypothetical model of individual vessels and a vessel coupled to a vascular unit and look at the anatomy now of the coronary circulation. We're going to look at just the left side by looking at the left coronary artery, which comes off of the aorta just beyond the aortic valve. The left coronary artery then branches to the circumflex artery, which supplies blood flow to the upper left lateral regions of the left ventricle. The left common coronary artery also then will continue down the ventricle as it forms the left anterior descending artery to perfuse the majority of the anterior and lateral wall of the left ventricle. The left coronary artery is said to be in series with both the circumflex and the LAD arteries because the flow from the left coronary artery is divided between these two sections. And so this artery is in series with this, and this artery is in series with its feed artery. Normally, these arteries show virtually no measurable pressure drop along their lengths because once again, these large distributing arteries have a very low resistance relative to their flow. So to keep things simple, I'm just going to say that the pressure, the mean pressure, arterial pressure in the left coronary artery is around 100 as it comes off the aorta. And even down to the point where it begins to branch into the circumflex and the LAD, the pressure would still be about 100. And further on down the LAD, or even out here on the circumflex, it would still be about 100 millimeters of mercury because the pressure drop is very, very small. Furthermore, I want you to note that the circumflex artery and the LAD artery are said to be parallel vessels. They're both coming from the same common source, so these are said to be parallel arterial segments. Therefore, the vascular beds supplied by the circumflex and supplied by the LAD are said to be parallel vascular beds. Let's now look at the effects of having a single stenotic lesion within the left coronary artery. Now, stenosis means a narrowing of the artery, so this could be due, and most commonly due, to atherosclerotic plaques that are forming in the coronary artery. So that's denoted here with these red lines on the inside that is producing a narrowing of the left coronary artery. So this is going to increase the resistance of the left coronary artery proximal to the circumflex and LAD branches. Now, by having this occlusion here, the pressure proximally doesn't change because that's going to be determined by whatever the aortic pressure is. And as long as the aortic pressure stays at 100 millimeters of mercury, mean pressure, which we're assuming it is, this will also remain at 100 millimeters of mercury, whether or not there is a stenotic lesion here. But because of the stenotic lesion, that decreases the distal pressures. So on the other side of this lesion, it's now showing a pressure of 80 millimeters of mercury. In other words, across the length of this narrowing of the left coronary artery, I'm depicting a 20 millimeter of mercury pressure drop. Now this fall in pressure decreases the effective perfusion pressure for both the circumflex and the LAD arteries. Therefore, both of these arteries will have reduced maximal flow capacity. But with a pressure of 80 millimeters of mercury, these vessels and these two vascular beds would still be able to dilate somewhat when needed to, but because of the reduced perfusion pressure, they will not be able to achieve the same high degree of flow increase when they are maximally dilated. Furthermore, it's important to note that with this fall in perfusion pressure to this vascular bed and this vascular bed, these vascular beds would normally respond by decreasing their resistance in their small arteries and arterioles, and that will prevent the resting flow from being reduced. So even though they have a reduced perfusion pressure, resting flow may be normal. And that is because of what we call autoregulation of blood flow, which the coronary system has a very high capacity to do. And autoregulation can be defined as the intrinsic ability of an organ to maintain a constant blood flow despite changes in perfusion pressure. Now in this slide, I want to look at a single coronary stenotic lesion, but in a different vessel than we did in the previous slide. In the previous slide, we looked at a stenotic lesion in the left coronary artery. Now we're going to look at what would happen if we had a lesion just in the LAD artery. It would also apply to if there was just a lesion in the circumflex, but I will use the LAD in my illustration here. If we have a lesion here in the LAD, distal to the circumflex branch, it's important to note that there will be no change in circumflex blood flow. It's very easy to think that, well, if you have an occlusion here, you're going to get more blood flow through here, but that does not occur. It does not occur because the pressure here, which is driving the flow through this vascular bed, is not going to change. This pressure is still going to be whatever the aortic pressure is, proximal to this location. And so the pressure gradient doesn't change, and if the resistance doesn't change in this vascular bed, there will be no change in circumflex flow despite having a stenotic lesion in the LAD. However, this stenotic lesion in the LAD will reduce the pressure distal to the stenotic lesion, which I'm showing here to be 80 millimeters of mercury. So a 20 millimeter of mercury pressure drop is occurring. Well, this is reducing now the effective perfusion pressure for the vascular bed being supplied by the LAD. And this will reduce the maximal flow capacity of that region of the myocardium. It turns out that this lesion may not necessarily reduce the resting flow, however, in this vascular bed, because with a reduced pressure, the vasculature will respond by decreasing its resistance and undergoing what we call autoregulation of blood flow. So therefore, dropping the perfusion pressure from 100, which it was without the lesion, to 80 will result in a fall in R sub S, which will help to restore normal resting flows. Now, if you have reduced resting or maximal flow in the LAD, or if this was a single lesion in the circumflex, in either case, that would reduce the resting or maximal flow, of course, in the feed artery, because it will not be supplying as much blood flow, either under resting conditions or in a maximally dilated state. Now let's look at the hemodynamics of a dual coronary stenotic lesions. Increasing the left coronary and LAD resistances, so now we're going to have our original lesion here in the LC plus our lesion here in the LAD. What that will do is to cause reduced arterial pressures distal to each lesion. So as before, let's make this 80 here, distal to this proximal lesion. And then distal to this distal lesion, we'll say that the pressure now is 60. So we have a 20 millimeter of mercury drop here and a 20 millimeter of mercury drop here. Because this pressure here is around 60 millimeters of mercury, we will be at the lower limits of our ability of this vascular bed to autoregulate its flow. Because at that low arterial perfusion pressure, the resistance here will be minimal. In other words, it will be maximally dilated at rest. And so therefore it has lost its vasodilator capacity. On the other hand, the circumflex, which is being perfused at a pressure of 80 millimeters of mercury, is not maximally dilated. It may be partially dilated by autoregulation, but it still has some vasodilator reserve capacity. So autoregulation decreased the resistance, but not causing maximal dilation as occurred here, and therefore it still has the ability to dilate if needed. It's just that the reserve capacity to dilate has been reduced. Now let's take this a step further. What happens if we now provide a vasodilator stimulus, such as would occur with exercise or infusing a vasodilator drug, such as adenosine or dipyridamole? Well, if we do that, either exercise or using vasodilator drugs, what will happen is that we will decrease the resistance in this vascular bed, which is still capable of undergoing vasodilation, and that will increase the flow through the circumflex artery into this vascular bed. That will then increase the flow across the left coronary artery in order to supply the increased flow to this vascular bed. As this flow increases, you're going to get a reduction in the pressure distal to this lesion. Remember that the pressure drop across a segment of an artery is directly related to the resistance. So if you have a high resistance, that would create our initial pressure drop. But then if you increase the flow, you're going to further increase that pressure drop. So now the pressure, instead of being 80, is only 60 millimeters of mercury. Well, that 60 millimeters of mercury now, that a further reduction in perfusion pressure through the circumflex will limit the maximal flow increase that is possible in the vasodilated state. It will still increase its flow. It will still dilate. But the fall in perfusion pressure as the flow increases will now limit the degree or the magnitude of the flow increase. As the flow increases across the circumflex artery and across the left common artery, and this pressure now falls, there also now must be reduced perfusion pressure to the LAD supplied vascular bed. And I'm suggesting that that pressure might fall now to 45 millimeters mercury, because if this pressure falls here and we have a stenotic lesion here, there still has to be a pressure drop across that lesion, and we have a lower pressure here. This pressure here might fall down to 45 millimeters of mercury. Well, at this very low perfusion pressure, going to a maximally dilated vascular bed, as we already described in the last slide, this will lead to a decrease in flow in this vascular bed. And this, by definition, is vascular steal. In other words, as flow is increasing in this vascular bed, it leads to a fall in pressure here, and therefore a fall in pressure here, and this is the pressure that is perfusing this vascular bed. And so that will lead to a decrease in flow just passively, because these vessels are maximally dilated, and if you decrease the perfusion pressure, you will decrease the flow, and that is called vascular steal. We can see from this model that vascular steal therefore requires both a proximal lesion and a distal lesion, and also a maximally dilated vascular bed that is distal or being supplied by this distal lesion. Furthermore, vascular steal results from a redistribution of pressures that occur between parallel vascular elements, so that as flow increases in one vascular bed, it reduces the perfusion pressure to another vascular bed, and because it's maximally dilated, it causes its flow to fall. Well, let's summarize what we have learned in this lecture. First of all, a single stenosis decreases perfusion pressure and maximal flow capacity of distal vascular bed. So for example, if I have a lesion here, just in the left main coronary artery, a lesion here will decrease the perfusion pressure and hence the maximal flow capacity of both of the vascular beds that it is supplying. Or if I have just a lesion here in the circumflex and no other lesion, that would reduce the maximal flow capacity of this vascular bed but have no effect on the maximal flow capacity of this vascular bed. Likewise, if our occlusion is only here in the LAD, that will reduce the flow capacity here, but have no effect on the maximal flow capacity in the circumflex vascular bed. Vascular steal requires a proximal lesion and a lesion in another distal vascular bed. It could either be in the circumflex or in the LAD. If it's in the LAD, then if you have the distal vascular bed supplied by the LAD that's maximally dilated, then you have the condition set up for steal where as blood flow increases here, it would decrease the flow here. Now let's look at this in the reverse now. By assuming that our lesion is in here and here in the circumflex artery, in that case this vascular bed would be maximally dilated. And so that as we increase the flow here in this vascular bed, it would reduce the perfusion pressure to the circumflex and cause a flow reduction there. So as flow increases to one vascular bed, flow decreases, or vascular steal, to the parallel vascular bed that is maximally dilated. And that occurs because of a decrease in perfusion pressure to the maximally dilated parallel bed.